We have two excellent speakers. So I'm going to introduce our first speaker, Dr. Stefano Merciai, and he is a consultant from, is that 2.0 LCA consultants, right?
Yes.
Yeah. And also you are a researcher at Leiden University in Netherlands.
Yes.
That's great. That's we look forward to your it's a very kind of unique combined background between both academic and the consulting field, which is actually very important for our field. And Dr. Merciai is an expert in input and output analysis, and in particular the hybrid version of the Excel base, where you actually made contribution over the years. And in recent years, you're working on the Bonsai.io, which is an open source web platform for calculating the product footprints, so which is also going to be the focus of your presentation. So yeah, without further ado, the floor is yours, Dr. Merciai.
Okay. Okay, so I start sharing the screen. First of all, I would say thank you very much for inviting me to this presentation and to have the occasion to present our work at Bonsai. Yes, I will start with the presentation. I'm Stefano Merciai, and I work, as I said, at 𝐂𝐲𝐜 and as part-time researcher at Leiden University. And this is, I will present today, is a project that will be finalized in a few months, and is could be considered as a kind of a follow-up project of the hybrid version of 𝐾𝐿 base. So I will talk about a bit of the introduction of this framework. I will also talk about some theoretical aspects, the principles that are guiding us in this project, and I will introduce the multi-layer framework that is peculiar of this database, and perhaps the contribution that would be nice to get from the industrial ecology community, and then the conclusion. So first of all, what is Bonsai.io? Bonsai.io is an input-output database that we are building within the Getting Data Right project that is led by Aalborg University and founded by the 𝐋𝐢𝐿ChR Foundation, that is a Danish foundation. Bonsai.io can be used for as a background database when you are doing LCA, so you can complete your system. You can attach Bonsai.io to your foreground system to complete your analysis. You can be used for footprint of products, but can also be used for impact of regions. So economy-wide analysis, but also can be used for scenario analysis if you want, for example, to model what is the change, what is the consequence of changing the electricity mix, fuel mix, or some disruption on supply of your system, and also, in typical analysis of input-out tables like the supply chain. So there is quite a flexible tool that can be used for many different purposes. Now I will introduce the general framework, because it could be that I'm mentioning input-out table, and these are not familiar concepts for industrial ecology. So I spend like a few minutes to explain what exactly is an input-output database. Perhaps you are more familiar with a graph or a chart where you have activities that are exchanging products. So it can be product, can be services, and then there are other agents that are consuming these products. This chart can be included in a matrix format. So if you have a matrix format where from one side you have the source of your flows, and on the other side, on the rows and on the column, you have the destination of your flows for activities, consumer. And then you have a matrix, and it's exactly what is an input-out table. So input-out table is nothing more the same information that you can have in a chart, in a diagram, but structured in a matrix. Of course, you can also have the exchanges with between the technosphere and the biosphere. So you have the emission, resource extraction, but you can also have the social spheres, or the use of labor, or the use of land. All this information can be structured in a matrix, and this is what is exactly an input-output database. So it's only a different way of collecting and using the structuring the data. Of course, I mean, if you have this exchanging between agents, you can have this exchanging in different regions, but you can also have that this agent in different regions are linked to each other, so via the trade. So you can have an import, export of products. What the resulting in the input-out table is that you have like a bigger matrix where you have more regions that are where you have like exchange between this region and the trade between the different regions. The same thing, you have emission, resources, land, and use of labor, but other extension. And of course, because it can be that these data are coming from different sources, from these different statistical offices, we need to operate some work. We have to reconcile, homogenize, and balance all the data. And so at the end, what we get is a multi-regional input-output database. So multi-regional input-output database can be, in like using industrial ecology words, can be considered as a big, like a huge technology matrix where you have the exchange between activities within and between countries. So to sum up, Bonsai.io includes extraction of materials, the transformation of materials, the consumption and the accumulation, and of course, I mean, the emission and the waste. And because we have waste treatment, we have also the loop back to the economy with the secondary materials, and all this in all the regions of the world. And now in Bonsai, we have 43 countries plus 5 rest of the world regions. Our wish is to include more and more countries in the future. So what are the main principles that are guiding us in this project? First of all, transparency. Because input-out tables are, I think, often perceived as a black box. So you have these tables, then you get some result, but you don't know what is inside, how it has been built. And we would like to break this perception, and so to create something that is more transparent. I will show you later how we think to do this. The same important thing is traceability of data, because for us it's important to show from what is the starting point, what is the raw data that have been used, and how this data is transformed till to the end when we get the final results. Everything that we are producing is open source, and so it's uploaded on a website, on GitLab, on a repository, and is using most of our code is in Python. It also is like open source language, and the idea is to have a database that is easy to update, so that there is can be maintained without big funding, and that can be every year we can update easily the database. And at the same time, we are also changing what is the structure of input-out database, so that to meet the needs of life cycle practitioners, so that we are inserting some concept that have been developed within the industrial ecology community, and so we are adapting input-out table, so to meet like really the requirement of industrial ecologists. And then, of course, we want to create something that is open to contribution from the community. In order to explain what I mean with the previous bullet points, I will introduce what is the workflow of Bonsai.io. 𝐾𝐿. First of all, we do a data collection from several data sources. So we use data from, we download data from FAOStat, from Eurostat, so all the main organization, because I mean they are already reconcile the data, homogenize the data. So for us, it's very important already to use these data sources that are very robust. And we have creating some APIs so that we can parse this data directly from the website. This is our collect phase. Of course, there are also some information that we cannot download, some data set that we need still to do some manual download. But the idea in the long run is to get rid of all these manually downloaded data and to just have APIs that are collecting data. So this is easily to upload, also to update to a more recent year without human intervention. And then we need to clean this data because they come from in a different format with different standards. And so the first procedure is to collect data and to clean it, to get in a format that is ready to be uploaded, to be used by Bonsai. Another big part is the life cycle inventory. So before the data collection from website is mostly the top-down approach, where we collect all data from data sources, that is production of steel in countries, the trade and so forth. But for us, it's very important also to have a bottom-up approach so that we can model properly what are product processes. And for this, we collect a lot of data from life cycle inventories and we organize in function. And all this information from life cycle inventories and from statistical offices, they go together in one code where we try to organize the data, to merge, to do the gap filling, and to operate all the operations that are needed in order to create a balanced database. And then when we have this balanced database, we can insert our transformation model. That transformation model just to input in industrial ecology languages, like, I don't know, we are implementing the allocation model or the consequential model, the system expansion, all different techniques that are used in input-output in industrial ecology. And then we get the input-out table. And from the input-out table, we derive what are the footprints of products. As I said before, everything is written in Python. This workflow that I have just explained now is uploaded on GitLab, so you can access the workflow, and then we run via, we use Airflow. I just show you the repository where we have the code of Bonsai. So this is open access, so you can see here there are different phases. I mean, I try to simplify the workflow, but here are all the steps that are on GitLab. So you can see the phase of collect where we have all the APIs. Then we have the clean and the build. So if you clean on the build, you will see how it can be created a balanced database. And then so you can see all the code that has been used in this project in order to create these tables. And we are also working a lot to write a good documentation so that it can be easily understood by a practitioner, where we can see like tutorials how to install these softwares and how you can even run on your machine, and all the theoretical part that will explain what are the logic and what I'm telling you now, but of course much more detailed. And when we are producing this balance table or input-out tables or the footprints, everything can be downloaded. So we are creating APIs that you can use It's taking a bit to load. But in this API, so you can download all the balance database. You can download the input-out table, the footprint, the contribution to the footprint, and so forth. So everything is easily, it can be checked and can be downloaded on your local machine and be used in your daily work. An important thing is the multi-layer framework. This is perhaps a peculiarity of 𝐋𝐢𝐿. Let's assume that in society you have so many different products, and each product might have some specific properties. For example, bread can have a weight, can have an economic value, can have a nutrient content of carbs and protein and so forth. And then we have different products, for example, fuel, that might have different properties. And so all the other products and flows that are like exchanged, produced in society or in the economy or between the technosphere and the biosphere, all these products might have some specific properties or their common properties. So what we are doing in Bonsai.io, we are creating a multi-layer framework. So each layer can be thought as one layer where we have one unit of measurement. So we have one matrix where we account all the products that can be accounted in monetary units. So for example, we have like so we can have, in this case, okay, I've lost we can have bread or fuels, cars that can be accounted according to the monetary layer. But at the same time, we can also have the mass layer where we have all the flows that can be accounted using unit of measurement, kilograms of tons. So we have bread, fuels, and cars, and so forth. And so at the end, the idea is to have so many different layers, and so a product can be in different layers according to the specific properties. And of course, there are some layers that can have more or less product, depends on the properties that are common between products. And the idea of this framework that we can expand as we like. We can have hours, items, square meter, whatever, and we can include all the flows that we have in different units. And of course, to move from one level to the other, we can use conversion factors that are, for example, price to move from mass to monetary layer, but we can have calorific values to move from energy to mass, and so forth. And each of these layers, because we are an input-out framework, this input-out table is very important that everything is balanced. Each of this flow of this layer, because it's accounted in one unit, is balanced, and so that we can respect the conservation laws. And this is purely what is the part when we about accounting, where we are creating and balance database. But when we move to the modeling, so we're more the calculation of footprint, we are reducing the computational need of this framework. So what we do, we select for each product one property. So in case, for example, of bread, we have ton. For case of energy products, we have only megajoules. So megajoules. For cars, we have items. For construction, square meter. So each product is accounted only on one unit, and this one unit is the natural unit of characteristic unit. So that at the end, we move from a multi-layer framework to a mixed table, and this will be our input-out table. But because our multi-layer framework is balanced in all the properties, our resulting input-out table will also be balanced. And so at the end, we can perform our model, our calculation of footprint using this input-out table in natural units that will be mixed, where each product will be accounted only following one unit. And this is exactly then what you do in the daily life with the technology matrix, where you are using more physical unit like kilograms or square meter and so forth. So we hope by doing so will be easier for the life cycle practitioner to plug the foreground system, and so that to link 𝐂𝐲𝐼O to your foreground system, and so that you can use for your life cycle analysis. So to sum up, the idea is to have a multi-layer accounting that where we create this balance table. Then we move to a model that is a mixed unit, where we only have one unit per product. And then we can get results in mixed units, but via the conversion factor, we can go back to multi-layer framework. And this is like the logic that we are applying in 𝐵onsai and in our calculator that you will see afterwards. And then what could be like, I don't know, the contribution from the community. 𝐵onsai, I said before, we use a lot of data, top-down data coming from statistical office, but also life cycle inventories. And so it could be that, for example, you are a PhD and you have done a great job in, like, I don't know, in your PhD, and you know a lot about, for example, cheese. You can plug this information in the repository on GitHub repository, and then this your life cycle inventory or your model of the cheese production can be part of 𝐵onsai. The same thing can be done with data. If you are providing a database, this database can be you can upload like an API or the data, and the data can be used by 𝐵onsai.io. And so that at the end, the result that another lifecycle practitioner or yourself that you are uploading the data can make use of your research or your research. And so the idea is to have the contribution from the community. Of course, I mean, we are writing the guidelines so that it can guide the practitioner to integrate their work in 𝐵onsai. And we are using the Git technology. So if you are contributing with the code, you will be listed as a contributor to 𝐵onsai.io. So to sum up, the idea is also to create this platform. So we are creating this platform that is open to the contribution. So you can contribute with the data on production, on trade, waste data, but also process function, I would say lifecycle inventories, and how the different technology can work, and so that we can have like a tool that is not anymore maintained and developed by a small group of people, but more something that belongs to community. So to conclude, so the idea of 𝐵onsai is to avoid to redo the data collection any time, so that we have more time for analysis, a flexible tool that can be used for life cycle analysis, mass flow analysis, and input-output analysis. So it's something that can be used by both industrial ecology community, but also from input-output community. And this way, I think that we can also enhance the interdisciplinarity and collaboration between the different research groups, because we can have, like I said, also the multi-layer framework can be developed by different research groups, and so that we have like one tool can create a bridge between the different community, and also like perhaps clarify the terminology, because if we are starting from the same database, it's easy to understand why and we get different results in different research. Right now, what we are now, we have creating a demo version of 𝐵onsai.io. And for the moment, what we have still is a beta version, is like a calculator where analyze it, you can click and you can select different products. Then there are different regions and of the world. And then here you can like analyze, and then you can get what is the footprint. Then you can click, and then you can say what is the contribution to the different product. You can even compare data. So you can take this case, you can compare barley with, I don't know, beans, and you can do your analysis, and you can see what are the differences. And then here is the contribution analysis, and then you can also click and you can go more into the product and analyze all the different products. So this is what we have now done. I mean, this is still, we are still working on Bonsai.io because this project will be finalized in 2025. And in June 2025, and after, I mean, it's still like something that has to be written. So we don't know how it's gonna, what could be bonsai in next year, in a couple of years, or how will be the further development. But yeah, our idea is to have a tool that is open source and that can be used by the community, and it can be something that is together developed. Yeah, this is everyththing from my side. And if you have a question, I might
Stefano. Yeah. I have two questions, but before that, I want to kind of let the audience ask any questions if they have. And I want to say I get to know the bonsai, the user interface a few years ago. So I actually used that in my industry ecology course, and it's a lot. It's very user-friendly for my students before they actually get into, for example, OpenLCA or even Brightway. So it's a very a good kind of interface for people to first get started with footprinting. Thank you for that. But it's really good to know under the hood about the methodology. So this is very informative to me. Yeah. So any questions from the audience? Feel free to just open your mic or type in question in the chat if you want. Okay. Probably let me first ask a question. So I think in your workflow, the first step of data collection is more or less automated, right? So because you have the API that you wrote to pull data from different sources. And then you also will collect the inventory data, which I guess is manual process, right? Oh,
yes.
So that's also something I'm really interested in, is how do we automate this particular process? Are you also working with some people, for example, using some, like, for example, data mining techniques, or even some recent progress in the GenAI where you can speed up that process as well?
Yeah, I mean, we are also thinking about how to automatize this process, because this is also in the long run, we don't want to spend so much time in collecting data. So now we are search for alternative path. We are also search for AI to see, but of course, the problem is at the first year, and is to create, like, I don't know, the initial year. Now we are working on 2016. So the idea also to create a time series. But right now, at least for the first year, is the human intervention is very high, because we need to understand how good is, like, the data that we get from AI or from parsing data from the web. So I would say that for the first year, for like tuning the model, we need a lot of human intervention. But the hope that is in the future, we might have these recipes that need little maintenance, because I mean, perhaps the technology cannot change so quickly. And so that we can still have, like, some data that can life cycle event that we can keep for some years, and then of course using like AI or other techniques to parse data and to speed up a bit the work of updating the recipes.
Great. So yeah, we have two questions in the chat. The first one is from Mata. I hope I pronounced her first name right. So the question is it possible to use the bonsai database in software such as CIMA-Pro and OpenLCA?
For CIMA-Pro, yes, but the problem with CIMA-Pro is not possible to work on the full database because CIMA-Pro has some limitation in the software. So we need to calculate. I mean, to have some pre-calculating results that then you can use in CIMA-Pro. For sure, you can use Brightway. So we are also building the importer for Brightway. So for sure, you can import the full database because it's also in Python. So it's like the same language of Brightway. I don't know exactly OpenLCA. We have not worked yet on OpenLCA. So I don't know how it can be used. But for sure, I mean, I don't know if you can upload the entire matrix or you need to do some pre-calculated results that can be handled by OpenLCA.
Yeah, so OpenLCA, I think, for example, Excel-based has the OpenLCA version. Basically, I think they link, the database in a way that it can be directly imported to OpenLCA. So, yeah.
Okay.
So data interoperability is always a hot topic in LCA, right? So, okay, so for the sake of time, we'll try to actually go over the next two questions and then move on to Dr. Yang Qiu's presentation. So the second question we got is from Professor Chen Zhang, actually. So the question is, what are the major challenges in balancing and reconciling different databases, and how did you overcome them?
Yeah, I mean, there is I think it's the most challenging task to balance because, I mean, you have a conflict of data and so yeah, at the end is I mean, we are still working to find a balance that is to balance the table because it's the conflict of data. Some data is I mean, from different institutions you get, I mean, the same trade, like, the same balancing is like there are countries that are exported is not exactly the same as the imported. So we try to use reconcile data when it's available, and when it's not available, we have our routine that tries to balance and given, like, I don't know, perhaps we give like more importance to specific data sources where we can consider that are more reliable than others. But it's like I mean, it's also case by case. Sometimes we can also derive data based on alternative sources, and then we try to indirectly adjust the data. It's a complex work that is, I mean, it's hard to describe, but I think it's the main task is the balancing in this Bonsai.io.
Yeah, and I guess when you publish the methodology, we will see more details about your heuristics about like how to make decision.
Yeah, I mean, there will be also the code. The code, you can also see the code online, and then you can see how we did it.
Great. So one last question from Paula. Are there economic or social data in a database that will allow basically like a social LCA or, life cycle costing, I guess?
Yeah, we will insert the value added so that you can use the both like in economic terms. So what is like I mean, what has been the value, the income that is distributed to the primary factors, but also the use of labor in hours so that can be used for life cycle costing and to value added chain, and also to have the impact on the social life cycle, the social LCA.
Thank you. Thank you again, Stefano. Very excellent presentation. And thank you, questions from the audience. So we will move on to our second presentation by Dr. Yang Qiu. He is an earth scientist at Joint Global Change Research Institute at the Pacific Northwest National Laboratory, PNNL. And his research focuses on the intersections across various human and Earth systems using integrated multi-sector approach. So I think both our presenters will give us the the presentation on the large scale analysis. Yang leads the development of global change analysis model, also known as 𝐃𝐿, and to enhance its representation of critical materials and minerals. And I think his current work aims to basically examine the implication of critical minerals and materials on energy system transition and supply security. So without further ado, the floor is yours, Yang.
All right, great. Thank you, 𝐿ChIn for the introduction. I just shared my screen. I hope everyone can see my screen and also hear me okay.
Yeah, okay.
Okay, great. So yeah, so it's great to kind of like circle back to this industry ecology community, because I basically did my PhD in this area, and I did a lot of LCA and MFA work during my PhD. So now my work is more shifted towards the integrated assessment model. But as you have seen, my current work is mainly focusing on modeling critical minerals and materials. So I think there is still a good connection with the IE community. So today is my great pleasure to present some of our work on this area. And I'm also presenting this on behalf of our broad team at the PNNL. Okay, so before I get into the technical details, I would like to give an overview on the kind of like higher level thought on of this work. So basically, as you probably know, at the moment, there has been a lot of discussion on critical minerals and materials. And one of the main concern is that the world is basically deploying a lot of these low carbon technologies, which requires a lot of materials, right? But the problem is that at the supply side, we may not be able to ramp up the supply as fast enough to catch up the demand. So our main goal is to basically capture both the supply and demand, and also some of the trade and supply chain of those materials within our integrated multi-sector model called Global Change Analysis Model, 𝐃𝐿. Because of this, once we can endogenize all this demand and supply, we will be able to analyze the economic feedback between the material and the technology deployment in the energy system, because we want to know how material supply availability could affect technology deployment, right? And also we want to know how demand increase of those material could affect the supply side. For example, where those materials are sourced, and also how price of those material could change if there is a demand increase. So that's kind of like the high level philosophy of developing this capability within 𝐃𝐿 to capture materials and minerals. Okay, since I guess probably the audience, I'm not sure how familiar you are with 𝐃𝐿, so I just want to give a high-level introduction of the model. So 𝐃𝐿 is basically an open source integrated multi-sector model that aims to evaluate the interaction between different human and Earth systems. So in 𝐃𝐿, there are several major sectors, including water, energy, land, socioeconomics, and climate. So in the model, basically each of these sectors are interacting with each other depending on this physical relationship that we input into this model. And then in terms of the global coverage, currently 𝐃𝐿 separate the world into 32 energy and economic region. So since we are mainly focusing on energy systems, the global coverage would be these 32. But depending on the sector that you are looking at, for example, if you're looking at a water sector or land sector, there are different level of geographic coverage. And for water and land, there are a little bit more high resolution for region coverage. And then in terms of the time scale, currently 𝐃𝐿 solve for 5 years. Each run is 5 year until 2100, but the user can determine the end year of the run depending on the research need. And also 𝐺CAM has the capability to run at a 1 year period. So the next slide, I want to briefly introduce the working mechanism of the model. As I have mentioned, the model currently have several major sectors, and in those major sectors, we have different service or goods products. And for each of those service and goods, there is a market associated to it. So the demand of each of those market are, for example, in energy, agriculture, or land. Those are mainly driven by socioeconomic factors, for example, GDP and population growth. And then we also have the supply side for each of those markets. And then the supply of those goods and services are mainly influenced by technology characteristics. For example, the cost of different technologies, the energy efficiency, and all those kind of characteristics are determining how the supply and the market share of those supply will be like. And then all these human activities within all this market will generate emissions, right? And that will feed into the climate sector, which will affect CO2 concentration, radiated forcing, and also the average temperature. So that's basically how different sectors are integrated and also working together. And essentially, when the model solves for each period, what it does is basically to find a series price for each of those markets so that the supply and demand of those commodities and the goods will reach a market equilibrium solution. So in this talk, I will mainly focusing on introducing you one paper that we published last year. It's basically trying to demonstrate this capability of modeling critical materials and minerals in 𝐺CAM. So basically, in order to capture the material demand, we are implementing several key modeling efforts in 𝐺CAM, because in the past, 𝐺CAM does not really capture material demand, especially critical mineral and materials. So this is something new that we recently introduced into the model. In the first step of our work, we have mainly focusing on capturing material demand across different sectors. For example, energy, also building. Within energy, we specifically looking at electricity, transportation, hydrogen, etc. So this paper is mainly focusing on capturing the demand in the power sector. So there are three main modeling steps related to this effort. So the first one is to introducing some subtype technologies for mainly renewable energy technologies, solar, wind, and also battery storage. Because in the previous version of 𝐺CAM, the electricity generation technology is relatively generic. It only includes more generic technology type, for example, coal, natural gas, refined liquids, nuclear, solar, wind. But as you probably know, within each of these renewable energy technologies, there are different subtypes. And each subtype requires different materials at different intensity. So that's why we're introducing different subtypes into the model so that we can capture this material demand more accurately. And we also we can also evaluate some of this material and the technology substitution with these new subtype technologies. And then the second step is to include several key materials that are important to the energy system. And we collect the material intensity data from different literature resources and use that as an input. So once the model estimates future technology deployment in terms of capacity, for example, for the power sector, that will be multiplied to this material intensity input to calculate material demand. And then the third important action we have implement is that, as you know, for these energy technologies, technology costs typically include different components, right? So for example, capital costs, operational maintenance costs, and for some fossil fuel energy technology, it also requires fuel costs. What we did here was to separate technology capital costs into two components. One is this material cost, and the other component is the capital cost excluding material cost. So this material cost is basically determined by the market price of those material and the material intensity within each technology. And then this will be a variable, and it will change depending on the material price and intensity. And that variable will then feed into this technology cost, will affect technology cost. And then technology cost will also determine technology deployment and market share. So that's basically how we implement this mechanism using material price to influence the technology cost and then technology deployment in the market. So in this study, we have basically developed a range of scenarios to represent either energy system transition pathway or material supply projection. So there are two main energy transition pathway which you can see here. One is a reference case, basically assume future energy system will be dominated by fossil fuel. And then another one is a RCP 1.9 scenario, which assume future energy system will have high penetration of low carbon technologies. And then we also consider different material supply projections because we want to know how material supply could affect the technology deployment in the power sector. So we have for example, one unconstrained supply case, basically assume future material supply is unlimited. And then we also have a different supply constraint case. In those cases, we basically assume different materials will just the future supply of different materials will follow the historical growth rate. And then, as you can see in this table, we looked at all the 12 materials we included, and also we looked at each individual materials. And then for the future supply projections, we looked at historical growth rate and then multiple of the historical growth rate, because we want to see how future materials supply need to increase in order to meet the demand. So a combination of this energy transition pathway and the material supply projection gives us around 72 total scenarios. But in the following result, I'm going to just show you a few of them to just demonstrate this capability. And also just one important note, at the moment, we are capturing this material supply in a relatively simplified way. As you can see, what we are doing is basically modeling the material supply constraint as an exogenous limit. Basically, we project future material supply, and that act as an upper bound in the model. And that upper bound of material supply will basically restrict how much demand can increase over time. And what the model does is that when we have this exogenous material supply constraint, the model will endogenously calculate a shadow price that is added on top of the material price input, which will increase the technology cost that requires those material. And that's how when technology cost increase, the market share of that specific technology will decrease. So that is basically how this material supply constraint restrict specific technology deployment in the model. But in the long term, we are also actively developing this material supply curve based on mines project data. And then in the future, we will use this material supply curve endogenously in GCAM to determine how material supply will be, and also how material production cost will change based on those supply curve increase. So in the next few slides, I'm going to just quickly show you some results from this study. So the first result I'm showing you here is the material demand under different energy transition pathway. So what you are seeing here in this figure is the material demand in the global power sector in 2020 and 2050. So in the 2050, there are two energy transition pathway, the reference case and the RCP 1.9 case. So basically, you can see when there is no supply constraint on materials, the material demand in the power sector will significantly increase, which is mainly driven by the deployment of different renewable energy technology and also the battery storage. And then you can see the type of material that dominate this demand is mainly steel and aluminum. And then the figure on the right-hand side is basically showing you the demand for these materials that requires relatively small demand, which are typically called critical minerals or materials. And then you can see their demand will also significantly increase over time, especially under the RCP 1.9 case. Okay, so the next set of results that I'm showing you here is how material supply constraint could affect the future deployment of technology in the power sector. So these two panels you are seeing here is the global cumulative electricity new capacity when there is no material supply constraint. Okay, so we have a reference case and then RCP 1.9 case. And then the panels on the right-hand side you are seeing here is basically showing you the change of those material of those new capacity, how that will change under different material supply constraints. So here we have copper, neodymium, graphite, and then all 12 material together. And then as you can see on the x-axis, each of those material, their future supply are constrained at different multiples of historical growth rate. So basically, the key message here I want to deliver is material supply constraint depending on the type of material, right? So the power system could respond differently. So for example, when copper supply are constrained at historical growth rate, you can see the total capacity will be reduced by nearly half, and that will occur for all kinds of power sector technologies. Because copper, as you know, is used in generally all type of electricity generation and storage technologies. But for other materials, for example, neodymium and graphite, those materials are typically used in specific technologies. So neodymium is mainly used in the wind turbine as the supermagnet. So you can see when neodymium is constrained at historical growth rate, the wind turbine is the main technology that will be affected. And similarly, for graphite, it's mainly used in lithium-ion battery. So when graphite is constrained, the lithium-ion battery will reduce their capacity in the power system. So basically, the key message from this result is that we find that material supply availability could be a very important factor to influence future deployment of energy technologies. So we also highlight that future energy system modeling and planning should really take into account this material supply availability in the modeling process. Okay, for the interest of time, I will just skip some of the slides. And then I do want to highlight some of the kind of like key research questions we can kind of like answer with this new capability in integrated assessment model. So as I have shown you in this study, we have been mainly looking at the demand side. And then we're currently gradually building up this material supply curve into the model. So in the future, I believe there are several important research directions we can explore. So for example, we can looking at the global and regional material demand in the next few decades under a range of scenarios with the variation of technology deployment, socioeconomic change, and also resource availability. And we will also be able to answer some question about how material supply availability could affect technology deployment in different sectors, right? So now I'm just showing you the electricity, but as we have transportation, hydrogen, building, and other sectors, we will be able to evaluate the impact on those sectors. And also we will be able to understand how different sectors will interact and respond to this material supply constraint. And last, we will also try to develop this capability to capture some of the trade and also supply chain dynamics of these materials. So in the future, we will also be able to understand how international trade will change for those materials depending on different policy incentive, tariff, and also trade restriction. And the last, we can also implement some of the supply and demand side strategy to help close the potential supply and demand gap. For example, technology innovation that facilitate technology substitution, material substitution, and also material intensity reduction, recycling. So all those kind of supply demand strategies, we will also be able to evaluate in this model to better understand their role in closing potential supply demand and imbalance. So I will stop here and thank everyone for the attention, and I'm happy to answer any questions from the audience. Thank you.
Thank you very much, Yang. And as before, so if our audience have any questions, feel free to type that in the chat or just open your mic and ask questions. I do have a few questions, so I will probably get started. And first I want to just kind of comment on this particular field of research, which is enhancing IAMs with, for example, material flow analysis. Is actually very popular, very hot topic in industry ecology. And so thank you very much for bringing us this very informative presentation on especially the energy system. So I think while people are typing in their questions, I will first of all kind of get a clarification question on the geographic resolution of the model. And because I know that some of my colleagues in Canada are developing 𝐃𝐿 Canada, right? So can you comment on, for example, how refined the resolution is for 𝐃𝐿 for different regions?
Yeah, of course. So I would say for the a default version of 𝐃𝐿, now, like as I mentioned, we basically divide the world into 32 regions in the world. But we also have regional version of 𝐃𝐿, as you just mentioned, 𝐃𝐿 Canada, and we also have 𝐃𝐿 USA. So those regional version of 𝐃𝐿 further disaggregate that specific country into either provinces in Canada, right? Or in the US, we further disaggregate US into the 50 states. So basically the regional version will still maintain the 32 global region, but it's just additional layer of detail for that specific country with the state or provincial level resolution. Yeah.
That's very helpful. And a related question I have is your market equilibrium. Now, if you look at, for example, state or like a provincial level equilibrium versus, let's say, country level, do you see any, for example, conflicts when you kind of try to balance the market? Is there any kind of potential conflict if I'm looking at, for example, British Columbia versus the entire Canada when I run the model?
I actually haven't looked into those like a regional version of model, but I would say because for even regional model, we do have like a material energy flow between different regions, right? So for example, 𝐃𝐿 Canada, there will be electricity like a transmission from different provinces, and then for commodities and services, there will also be trade. So I think with those trade and like energy flow across regions, we should be able to balance those equilibrium well. Does that answer your question?
Yes, and I probably missed this. Is the market equilibrium? So what's the mathematical, for example, function or mechanism you apply in solving this equilibrium? I think that's kind of the cornerstone of the model, right?
Right. Yes. So basically, in GChem, we use like a probability approach. The method is called logit equation. So the logit equation is basically determining the market share of different technologies and also the trade of those commodities. And what it does is basically it take into different technology characteristics, for example, cost, and also, so cost is a very important factors in determining those market share. And also we have another parameter that capture all those non-cost factors. For example, maturity of the technology, societal acceptance. So we call it share weight. I would not go into detail of that, but basically we are using these parameters like a cost and non-cost parameters in this logit function to determine what is the market share of different technology and also how they trade within different regions. Yeah.
Okay. Thank you very much. That's very helpful. And I do have another question, but let me see if there's any question in the chat. Right. Not yet. So probably let me ask my question. I'm always interested in basically the interface between, for example, if you have an MFA model and GChem, right? So can you probably speak to, at a very high level, how these two type of models can interface or interact in your case?
Right. I would say at the moment, we are basically trying to adopting the MFA methodology in GChem, right? In the past, I think for MFA, we are just using material intensity data, and then we coupling that with some technology deployment projection or energy transition pathway to understand how material flow will be look like under those energy transition pathway. But I think what we are doing is to endogenize this material flow analysis methodology in GChem. So for now, we focus more on the demand, which is the inflow, right? But in the future, we can also estimate the stock and also end of flow because we capture the technology lifetime within the model. So we are able to model the stock and the outflow, end of life flow. It's just we are not really quantify those at the moment. But I think, I think our work at the moment is mainly, like I said, endogenize this material flow analysis methodology in GChem to expand our capability to represent the materials. And also one benefit of endogenize this methodology is that we can use the model to determine not only how supply affect demand, but also demand of how demand will also go back to affect the supply. I think that's the key insight that I think this coupling can provide.
Yeah, so you're speaking to the feedback, right? So the endogenous feedback loop, because my experience is that you can have exogenous variables. For example, you can have some very general terms for variables such as GDP and other like big brush kind of variables, and that's going to determine, for example, the market share of the technology. But from bottom up, you may have, for example, some constraints, not only on the material side, but also a lifetime, right? So for example, if you have a existing coal power plant, right? So this is going to have a much longer lifetime. Then even if there is a kind of exogenous variable saying that we want to have more wind turbines, it's probably not going to happen because you don't have the resource to invest in another wind turbine, right? So that's something GChem is trying to basically capture.
Can you repeat your question?
Yeah, I was like, for example, you will have the exogenous variable that determines, for example, we will have more wind turbine in a particular region. But also, if you look at what already exists in a region where you have, for example, a coal power plant that has a very long lifetime. So this means you will not be able to invest in the wind turbine in that
Okay.
case, right? So there might be some conflict. If it's like a top down and bottom up modeling approach in this case.
Okay. Yeah, so I would say, so basically, let's say for power system, all those technology deployment is actually determined within the model. So we don't really have like a exogenous constraint or incentive to say how wind turbine will change. So the deployment of wind turbine and also coal power plant are all determined endogenously within the model. And speaking about the lifetime of coal power plant, we do have a kind of like a parameter which is called like a related to profit of those coal power plant. So if the profit of the coal power plant decrease, those coal power plant will actually retire earlier. It's kind of like become a stranded asset. So let's say if we have a like a policy, like a carbon price, let's say, right? So that will kind of like increase the price of the coal generation, and then the coal power plant is not making any profit anymore, then it will retire earlier. So all those kind of technology deployment and also retirement is actually determined endogenous within the model.
Thank you. That's very helpful. Because I was thinking about, because traditionally MFA, you only in many cases only think about the physical attributes of a power plant, right? So it will stand there as long as it can be functional. But yeah, in your case, you also account for example, some policy implications that make it more expensive than you're gonna retire early. Thank you very much, Jan. And I guess I asked a lot of questions.
I think those are great questions.
And thank you both our presenters for your very excellent presentations. I think in both cases you basically show us the tools and the platforms where we can actually do large scale analysis for sustainability. As I mentioned earlier, these two presentations will be uploaded to ISIE's YouTube channel in probably a week or two. So if you want to rewatch some of the details, you feel free.